Okay, perfect, guys. For whoever hasn't met me before, my name is Vincenzo. I work in Crete, in Action, in Greece. Okay, today we will talk about some meta-analysis approaches for omics data. I have to warn you that the presentation will be particularly boring and technical and mathematical. So this means that you were very lucky you had before the coffee break, and now there is a presentation. Otherwise, if the presentation was this evening at 5, I doubt anybody will have survived. So, since we are lucky, we are here in this nice place, and we have this fantastic presentation now to do. Okay, let's start to go, and let's see a little bit what we are going to talk about today. Okay, first of all, let's see a little bit what is this meta-analysis, this obscure object, and what we are going to talk about meta-analysis. Let's see a little bit how we can apply this in omics. So let's see why we are so interested in meta-analysis when we want to analyze omics data. Then we will just review a little bit what are the meta-analysis approaches. I'm not going really into detail actually here because there are many of them, and interested people can then make some research by their own. There's also some alternative meta-analysis when it comes to omics data. And finally, we have a summary with some take-home suggestions. Okay, so as usual, when I try to find definition of something, the first thing that I do personally is to go on Wikipedia. So when David told me, okay, you must make a seminar about meta-analysis, the first thing that I've done was go on Wikipedia, what was it is about. So essentially, this is a pretty much general definitions, just talking about, okay, we have different studies and want a little bit understand what we can get by combining these studies. Okay, let's be a little bit more specific, and let's see a little bit what is the setting that we will consider here. What we are going to consider in this case is this. We have several studies that they can be performed in different times, in different years, for example. All these studies, anyway, they try to answer the same question. For example, they try to identify differential expressed genes in two specific conditions, like Alzheimer's versus controls. Each study has its own different samples. So each study was, for example, there was a study in Spain or a study in England and so on. And they should also have the identical study design. For example, all case control or retrospective studies and so on. This is the setting we are going to talk about today. Although other settings are also possible, but they are more complicated, I'm not going to touch it. So, having in mind these specifics, let's see a little bit exactly what we want to achieve with the meta-analysis. So essentially, from each study, I get one different dataset. In this case, you can think of a dataset as just a matrix. You have for each row be a patient, and for each column a measurements. So what happens in meta-analysis is that usually I investigate my question of interest on each single dataset in isolation, and I get some statistics, let's call this C, and a p-value, let's call it P, that essentially answer the question I'm interested in. So, for example, C can be the fault change for a given gene, while P can be the p-value related to this fault change. And I can do this separately for each single dataset, getting, of course, one statistic, one p-value for each study in this case. Then there is, this meta-analysis method that essentially is some type of mathematical approach that allows me to take this big evidence and to summarize them in a single statistics and a summary p-value. So this is the main idea of meta-analysis, at least for what we are going to see today. Okay, so this is the schema that we are going to follow. So now let's see a little bit how to apply this schema on omics data. What type of analysis we can do in this case. Okay, this is a nice paper. Essentially, in this paper, they were studying essentially some properties of in mouse in the case of breast cancer. So in this case, what they've done is it was to take blood sample from mice, and they were measuring the expression profile in each mice. In some mice, they induced breast cancer, other ones were healthy, and in this setting, it's just to find the differentially expressed genes. So, for example, if you focus on first gene, you can find here the p-value about how much this is differentiated, for example, with the T-test or so on. And so let's say this is a very typical analysis. I put on purpose this p-value here because this is a nightmare of any statistician. Because when it is 0.051, you never know whether to call it as significant or not. Actually, I don't know why it is so different from 0.049, for example. Another interesting thing that they've done in this study is that they collected a second set of expression profiles, again between cancer and healthy subjects. And okay, they did a different type of analysis, but what they could have done was to make again some differentially expressed analysis and getting some p-values. So here I have, I don't know, 10,000 p-values, how many genes there are. Here, other 10,000 p-values, how many genes there are. And so I have two pieces of evidence for each genes. So what I want to do with meta-analysis is just to take, for example, the two p-values for the first genes and combine them in a single one. This is actually the p-value that you get if you use the Fisher method. We will see it later. And I can do it. I can do the same for all genes. And so at the end, I just get 10,000 p-values. These are the combination of this one. So this is just an example of how things work in meta-analysis. But this is a very tricky example now. Why? Because these two data sets that are real, they are on Zio, you can download them and you can perform this analysis, are actually pretty much different. These are from mice, from mouse model. These are human patients. And so the question now is, okay, does it make sense here to make meta-analysis? To be honest, I don't really know. I don't have an answer for this. Although we can generalize this question and we can say, okay, let's say that these were not mouse and humans. Let's say that there were two sets of humans, but one, for example, collected in Scandinavia and the other one in South Africa. Will it make sense to make meta-analysis? Well, this really depends by your question. So but this is a general question. I mean, when I have a different set of data, I have sets of data, I want to combine them. Does it make sense? Well, this really depends by the question that you are studying, and not so much actually from the method you use, the fat removal or whatever. This was just an example of differences expressed genes, but for example, there is also other applications about meta-analysis of omics data. For example, when you want to estimate gene correlations or interactions, again, you can have different studies. On each one of these studies, you can record, for example, the correlation, and then you can combine these correlations. One thing that is not very used, but would be very useful, for example, is to estimate the gene variance. So again, you can estimate the variance on each single study and combine the different variances, and so on. In general, whatever you can do on a single data set, you can do on multiple data sets and then try to combine it. So then there is one more question that is even a little bit more ambiguous, that is horizontal versus vertical integration. So horizontal, okay, let's put ourselves in a very simple case. Let's say that we have made a multi-center study. So we have collected patients from different universities or laboratories around the world. And so we have our gene expression matrices, or whatever matrices, this can be proteomics, whatever. And so essentially we want to combine them. So different patients, but equal measurements, equal study design. That is essentially the ideal setting that we were discussing at the beginning of the presentation. So this we can call this horizontal integration, that essentially we are working in the ideal situation. Then recently, especially with the STATegra project, we came out also with something that is a little bit different, that is vertical integration. So first of all, thanks to Francesco for thanks to Francesco and I guess for annulling borrowing me their figures. So essentially, this is a case where I have different studies on the same type of data. Then another question is, for example, can I use meta-analysis also on different types of data? So does it make any sense, for example, if I have gene expression, methylation, proteomics, to apply here meta-analysis? Again, this really depends by your type of study and what you are asking for. Because, for example, let's see here what happened in the horizontal case. I have different genes. For each, I have two datasets for different genes. And let's say that these are just p-values from differential expression analysis. And so here it's very straightforward. Okay, I have these p-values. I just combine them. That's it. No problem. I mean, this is the ideal situation. Then the problem is what happens when instead I have something like that. I have differential expression for gene 1, I have a p-value. Then somehow, and this is also a very long discussion, I calculate a p-value for the differential methylation of gene 1. Of course, here, as we have seen yesterday, I have to decide what is methylation and what is differential methylation for the gene. What does this mean? I'm going to look on the whole gene, only on the promoter, and so on. But let's say we decide about that. And then the point is, okay, does it make any sense to apply meta-analysis here? Well, of course, the point again, the question again depends by your goals, depends by what you want to understand. Discussing about it within STATegra, we came out with the idea that if you apply meta-analysis in this case, you answer a different question. That is essentially, you want to understand whether the condition you are studying, whether this is E-cross overexpressed or not, or breast cancer, whatever. You want to understand whether this condition affects your gene in any possible way. So we want to understand whether this gene was affected by your condition in any possible way. And so if this is your question, then yes, it makes sense to apply meta-analysis and to try to estimate a global p-value out of this. And something very useful that you are trying to understand how much it holds, at least in STATegra, is this, that with meta-analysis, if you have two data modalities that are relatively significant or very significant, you can get more power by combining them, and so you can somehow have more findings to concentrate on. But again, there is not a univoc and simple answer. This really depends by what you are studying. Okay, having said that, let's see a little bit about so what we can do here. Okay, the first thing, and I put this first mainly because for historical reasons, is the summarizing p-values. So you have different p-values for a seminal hypothesis from different studies, and you want to summarize them. And one possible method is the Fisher's method. It's actually from the 30s. That is a method in order to combine p-values. So here, the only thing that you want to understand is whether your findings are significant or not. That's all. Then you have instead emerging effect sizes. Here the question is a little bit different. You don't want to understand only if your findings are significant. You want also to estimate what is the biological relevance, what is the biological effect, how much your condition, whatever you are studying, has an effect. And then, okay, these ranking methods are not often listed as meta-analysis approaches, but when you want to perform meta-analysis, you can also combine ranks instead of statistics or effect size or p-values. And we see also different ways in order to integrating ranks. So, let's see a little bit. Okay, let's start with some boring mathematical stuff here. And so, let's see a little bit how the Fisher method apply. So, as we said before, we assume here to have p-values that are independent from each other, as we were pointing out before. So this usually holds as soon as you have different unrelated samples in all studies. And then, okay, in order for this formula to hold, you also assume that all the null hypotheses are true. If this is true, then taking the natural log of your p-values and summing them will follow a chi-square distribution. So this is an ugly mathematical formula, but if you go back to our previous example and we take these two p-values, let's say that are both for the BRCA1 gene, then essentially all that we have to do in order to assess the combined statistical significance is to plug in the formula, getting a chi-square value, and check how much this chi-square, where this is placed on the chi-square distribution, with the 4 degree of freedom in this case. And this area here is just the p-value. I started all the presentation assuming that everybody knows what is a p-value, so I hope it's okay. So one thing that we actually discovered over that we noticed about this particular formula, Fisher formula, or in general about any meta-analysis that combine p-values, is that there are some tricky points about the use of asymptotic or zero p-values. So in general, using zero p-values, combining them will give you zero p-values. So essentially, a zero p-value can definitely shrink down your significance to the level 0. Not only that, in a publication that my colleagues had in the European Conference on Machine Learning in 2010, they were trying to use meta-analysis methods in order to learn based on networks, and they were making a lot of simulations. In this simulation, what they had is that when you have a lot of data sets and you use some asymptotic p-values, this actually can give pretty much wrong results, for the simple fact that you combine between them asymptotic p-values that are not extremely precise, and combining a lot of asymptotic p-values can lead you to pretty much wrong results. So it's also a small problem to take into account when you use this. Okay, so this was about combining p-values. What happens when we try to select to merge different effect sites? So let's again assume that I have 3 studies. Each study essentially estimates a particular statistic called the C1, C2, and C3. So in the fixed effect model, what I assume is that these 3 statistics that I have estimated are an estimation of the real effect called the mean. What also assume is that this estimation actually they follow a normal distribution with variance sigma. And so essentially in formula, all that I have here is that C will be equal to me. So what I estimate is equal to real effect size plus 1 error that is normally distributed. This is a very convenient formulation because essentially following this formulation and assuming normality, it came out that actually me can be estimated from the statistics following what is essentially a weighted mean. So I take my statistics, for example, this can be the fault change, C1, C2, and C3 can be the fault change for the BRCA1 gene in 3 different studies. I want to combine them, and all that I have to do is to take an average mean of the statistics. Sorry, a weighted mean of the statistics, where the weights are actually inversely proportional to the variance of C. In other words, I take C1, C2, C3, and I average them, taking into account that each estimation has a different precision, has a different variance. So I give more weight, more importance to the estimation that is more precise. Another good thing about this formula is that essentially, in this way, you can merge pretty much all possible statistics provided you are able also to provide estimation of the variance. For estimating the variance, there are some, again, ugly mathematical formulas. For example, here for the difference between means, I have the square root of the summation between the sample variance. But these are, again, mathematical formulas that are given. Or if you don't have this possibility, you can still, again, use some bootstrapping technique in order to estimate them. These are the fixed effect models. And this, let's say, it's the simple way in order to merge effect size. Good, but this is a pretty much, let's say, simplistic assumption. So let's see, there's also another type of method in order to estimate, to merge effect sizes. It's called the mixed effect models. So in this case, I start from a different assumption. I start from the assumption that my study is not estimating that my study is trying to estimate a given effect size called theta. So my study actually tries to estimate theta, and this is the effect size that my study is trying to estimate. Unfortunately, in my study, I have some, for several reasons, simply for sample size reason, I have some variance. So what I will measure will be C. So I measure C, and C is the estimation of theta. On the other hand, essentially in this model, there is not a single unique effect size for all the studies. Each study will have a different theta, and we assume that this theta will be essentially the effect size of the study. Let's take an example over this. Let's say again that I want to investigate the fault change in breast cancer against normal control of the BRCA1 gene. So in humans, this will have a effect size equal to theta. I make a study, and because for sample size, I measure something called C. But what happens is that if I repeat this analysis for another type of mammals, for example mouse, the theta will not be here, but for several reasons, for biological reasons, will be here. Again, I'm studying the effect of BRCA1 on cancer, but will not be here, will not be theta 1, will be theta 2. And this for the simple fact that the effect that I'm trying to study is different across studies. How much this is complicated? Who think that I should have use a better figure? Okay, essentially this means that I perform a study that tries to estimate theta 1, and I measure C1. A second study will never ever estimate theta 1. The second study, for several reasons, will essentially have a different effect size to estimate. And all that I see is that the various theta that are here, they are distributed normally again. So this is a pretty much not clear figure. I apologize for this. If you have any question, or even later I can explain it better. But so essentially what is the nice thing again about these formulations is that even if this is a slightly more complicated formulation, it brings to a similar formula. So again, in order to estimate me, I have to simply take an average of the estimated effect sizes, again weighted for the inverse of the variance. Although in this case, I also consider the variance across studies. In this case, we have seen essentially there are two different models for estimating the effects, for measuring effect size: the fixed model and the random model, and mixed models. Point is which one to use. If you think that in your analysis, in your studies, are unlikely to measure exactly the same effect size, you should use the mixed effect models. Although another caveat here is that in this case you have also to estimate tau square, that is the variance across studies. In order to do this, you need a relatively large number of studies to do that. Okay, finally, let's go to the integration for ranks. So this is a pretty much easier and sometimes also more effective method that essentially postulates that instead of integrating fx sides or p-values, it's better to integrate the ranks. So again, let's assume that I have two different studies with two different datasets, and I've estimated some p-values from both studies. What the integration ranks postulate is that in order to integrate these two vectors, these p-values, what I have to do is to convert them in ranks. So the lowest p-values get the rank number 1, and so on, in both datasets. So this is a pretty much simple transformation. And then what can be done in order to integrate these ranks is to take, for example, the product between the ranks, or the mean, or something that is pretty much similar to the mean, the sum of the ranks. So what happens here is essentially that with a simple function, I have essentially merged different ranks. So in the case of the product, what I can see even from this simple example is that taking the product will essentially give me dramatically larger a larger variation in my final statistics. So here I range from 3 up to 49. But try to figure out to have ranks that span from 1 to 10,000. When you take the product, you have numbers that go up to the million or billion. So this means that your distribution of the final statistics will be pretty much skewed. So you have a very big difference between the first ones and the last one in the final rank. And this is a little bit less strong when you go to the mean or to the sum of the ranks. So okay, in this case, I have, for example, that this particular gene is the one that is the most it comes first in my rank product. But what this means, is this any significant or not? The significance of this. So how to estimate the significance? Usually they use some permutation-based method with the ranks. Recently there are also some closed form expressions, especially for the rank product. But in general also one must understand that what it means significance when you go for the rankings. Because essentially your null hypothesis here is whether the gene has a lower rank than the one observed. That is a slightly different null hypothesis than whether the gene is a different expression or not. Okay, who has experience with permutation-based? There was only one hand. Okay. Okay, no, in general I was asking the audience. Okay, so here a little bit what permutation looks like. Again, I start from a study. I calculated my p-value for different expressed genes. I transform them in ranks. What I do then is to permute the labels in order to destroy essentially the link between my outcome and my measurements. I recalculate again the p-values or the statistics, and again I calculate the ranks. So in a permutation based when I perform a permutation based test, all that I do is to repeat the permutation several times, each time randomly, and each time I calculate the ranks, and my final p-value, in order to understand whether this rank is really the first one, I just try to understand how many times, I just sum how many times in the permutations I get a rank that is lower than this one, lower or equal. So that's all about the permutation base. I don't know if this is new for anybody. Doesn't look like so. Okay. Okay, so alternative to meta-analysis. Here will be pretty much fast regarding how to use these alternatives. So essentially this was actually the question you performed first. I mean, why not to take the different datasets, merging them, and then calculate the statistic here. So we passed already answer to this question. The problem is that it's not always possible. Okay, let alone when you have a batch effects, you can still try to adjust for them with some scaling or with combat. It's actually a method that was published in 2005. I should have put the reference here. I will put it later in the final version of the presentation. But this is not the only problem. For example, okay, in omics data, usually you have the same scale for the data. So, for example, gene expression is always calculated in the same way and so on. But try to figure out, for example, if you have, try to figure out, for example, if you have a data set with an expression from Affymetrix, another one from Illumina. How much it is meaningful there to merge the two data sets? Can you do it, actually? Maybe yes, but anyway, you have to at least to apply some method in order to make it possible. It's not always given this is actually possible. So this regarding the merging data. So I'm going to present a work that we have developed inside STATegra that we called HolistOmics, a pretty much nice name in my opinion. I'm not the one that invented it actually, but anyway. So essentially, this work here was coming from the problem we had from the settings we had in STATegra. So different type of data. Okay, we didn't have a macro array, but nevertheless different type of data, and we want to somehow to merge them. And again, here we want to perform a vertical integration. So in order to do that, let's say what we have here. We have different modalities on the same sample. So yes, we have exactly the problem before. That is the same sample, so they are related and so on. And essentially, we have microarray analytic proteomics data. I have different genes, and for each genes I have a p-value. Again, we have the same problem: how to calculate a p-value for a gene given proteomics data. These are all somehow solvable, this problem, but of course you have to find how. You have to have a policy and to follow it. And again, we would like to understand, okay, but at the end of the story, this gene has been affected somehow by the condition I'm studying, or better, has Icarus anyhow changed anything in this gene on its byproduct? Can I quantify this in a global way? This is the question. How much this is biological relevant, meaningful or not, this can be discussed, of course. One possible method are ranking methods. Meta-analysis method cannot really be applied. So essentially we came out with something called non-parametric combination. It is actually a known statistic for similar cases. For cases when you have essentially known dependencies among the p-values, and it's a permutation-based approach. So in the case of the non-parametric combination, what I have is an initial global null hypothesis that I can structure among different null hypotheses. So the global null hypothesis is that there is no difference in any of these data modalities. And so the single null hypothesis is there is some difference in microarray or in RNA-seq or in proteomics. And this MPC use a method that takes into account that these p-values can be correlated among each other. So does not require that the p-values are dependent, and also accept that they were derived on the same samples. The curious thing is that there are books and papers about non-parametric combination, but this is pretty much unknown in biology. So anyway, so what happened here for non-parametric combination is this. Let's focus on only one gene. I focus on only one gene, and through some permutation approach, I calculate the permutation p-value. Then I use some function. And when I say some function, I don't mean any possible function. There are a restricted family of functions that I can use in order to combine the p-values. I obtain the combined p-values, and I do the same with all the permuted ones, with all the permutations. So then what happens is that I have a null distribution of the combined p-values, and out of this I can calculate a p-value of the p-value in order to assess the significance of my global null hypothesis. So the cool thing about this non-parametric combination is that it matches the problem that I had at the beginning, that is essentially correlated p-values estimated from the same samples, and also gives me a p-value in order to assess the global significance of my reasonable null hypothesis. Okay, just shortly about the function I can use here in order to combine the p-values. I can use essentially the normal one, the Fisher, the one we have already seen, and this essentially, or I can use tippet, that is essentially the mean p-values, or liptag. I don't remember now the mathematical formula for the liptag. But another thing is this: if I use tippet, essentially I look for genes that are differentially expressed in at least one data modality. So one data modality is enough here in order to claim that gene as differentially expressed. If I use another function called liptag, then in that case I have to have support from all data modalities. And finally, Fisher as an intermediate behavior between the two. So we are almost done. We have a summary here. So just some take-home suggestion. Okay, about meta-analysis in omics, you can have horizontal. This is the most common versus vertical integration. This really depends by what you want to study. You can decide whether to integrate p-value statistics or ranks. Again, this depends by what you want to see, whether your findings are just significant or how much effect they have, or just if you want to have a ranking of your findings. So you say, okay, I don't really care about how much is the biological effect. I just want to know, for example, the first 10 genes. So it's better to use ranks. You can always consider some alternatives, for example, batch effect removal. One more thing about packages in R. So in CRAN you can find several packages for meta-analysis. What I usually employ is either metaphor, it is pretty much generic, or metacore, that is more specific for correlations. Or if you have directly gene expression data with some expression set and so on, you can consider some of these bioconductor packages. MAMA is pretty much a collector of different of other meta-analysis packages. Also MetaDA, meta differential expression, also implements pretty much a large number of meta-analysis methods. And what is most interesting is meta quality control, that actually allows you to understand whether you can apply meta-analysis or not. So some quality control analysis. Okay, so this is just a final remark about my experience so far in this in this summer school. So essentially, this is a Maslow pyramid about the needs of humans. So first food, then safety, social need. And what really struck me is that we risk our safety walking for 2 kilometers under the rain in order to get the Wi-Fi. So I guess yes, actually yes, Wi-Fi is more basic than a lot of things. Okay, so any question? So I assume my presentation was a success. Thank you.